Hey guys, welcome back. So about 2 weeks ago, I was at the Codetalks developer conference in Hamburg in Germany, and I was a speaker there, and I gave a talk on an introduction to return-oriented exploitation on ARM64. So this is actually the same talk I gave at another conference a couple months back in Manchester, which some of you guys may have already seen by now. But I just wanted to make this video to quickly talk about this conference and actually show you the talk. So I've been given permission by the conference to upload the talk onto my own YouTube channel. So for the end of this video, you'll be able to watch that 30-minute talk if you're interested in it. And yeah, so it was a really great conference. We was over there for 3 days, and the conference took place for 2 of those 3 days. And there was a lot of people there who I've seen from Twitter before, who I've sort of met online. There was a lot of great talks on, and there was lots of free food. There was an after party and a dinner, and it was a really great conference overall. So there'll be a few pictures on the screen now showing some of what was going on. But yeah, so I just wanted to upload this talk so that all of you guys can see this from my main YouTube channel, because it is also uploaded on their YouTube channel, the Codetalks channel. But that's not really got as many subscribers. And I was thinking that since I got 34,000 subscribers on this channel, who haven't actually been notified about this yet, because I've actually only tweeted this, where I've got about 17 or 18,000 followers. So I just thought I'd put it on YouTube as well, just so that, to maximize the amount of people who actually see this talk. Yeah, hope you guys enjoy the talk, and thanks for watching.
Alright, so hello everyone. I'm going to be talking about an introduction to return-oriented exploitation on ARM64. So this can be for anyone who is unfamiliar with software exploitation and vulnerability research. So first of all, a bit about me. I'm an 18-year-old. My name's Ellis. I'm from the UK, and I've been doing iOS app development and programming for around 5 years now. And recently, in the last 2 years, I got interested in security research, mostly from a point of view of iOS jailbreaking, and I've studied that for the last 2 years. And during that time, some of my work, I've created various set of different exploit challenges. So these are basically small programs that you can download and try to hack, essentially, by writing different exploits for different kinds of memory corruption vulnerabilities, and those are all available online. I'm also the author of 2 books, the Beginner's Guide to Exploitation on ARM series, and these books essentially go through the exploit challenges, the programs, and it kind of explains them all in different chapters aimed at complete beginners with no experience with reverse engineering and software exploitation. And I also run an educational YouTube channel where I teach various different programming topics, jailbreaking, things like that, basically. And that's been going on for as long as I've been doing app development, so that's about 5 or 6 years. So the focus of this talk today is going to be to, as I said, introduce return-oriented exploitation techniques for people who are unfamiliar. Also going to cover the fundamentals of the ARM and ARM64 architectures. And I'm going to, at the end, demo an exploit using some of the techniques I'm going to talk about, just so you can kind of see how it would all work in an example. So first of all, why would you want to target an ARM-based device? So if you don't know what ARM is, this is the chip that is used in all mobile devices and embedded systems. Some laptops are using it as well. And in the last decade, these have become more and more popular. You see mobile devices everywhere and people using them for more things than they used to. And therefore, this makes this quite a big target for malware developers and any kind of attacker. So the fundamentals, we're going to start with the ARM v7 instruction set. So this is the 32-bit ARM instruction set. It's a 32-bit RISC architecture, and it uses instructions of a fixed size of 32 bits. It also supports a different mode known as thumb mode, and that's basically a 16-bit mode, so you can use that for like memory efficiency and stuff. And you have 16 main registers that you need to know about as an assembly programmer. So these registers are labeled from R0 up until R15. Now the first 13 of those, so R0 to R12, these are all general purpose registers. So you can use these to hold any values that you need for calculations. And the first few of those are used to pass arguments to functions. So unlike some other architectures, on ARM, you don't pass arguments on the stack. You pass them directly in the registers. And then we have some special purpose registers. So R13 is the stack pointer, which will always hold the address of the top of the current stack frame. R14 is a link register, which will hold the address of where code execution needs to resume after a function is finished being called. And finally, R15 is the program counter, so this will always hold the address of the next instruction that needs to be executed. On the other hand, we have ARMv8, and this is the 64-bit version, so this is also known as ARM64. And it's a 64-bit version of the ARM architecture. The chips do support 32-bit version, of course, so you can actually do backwards compatibility. And there are some additional features in these processors, such as exception level support. So you can kind of physically separate code executing to add for additional security features. And then with the registers on ARMv8, we have a different set of registers. This time we have 30 general purpose ones, so quite a few more. And these are labeled with X's, so we have X0 to X29. And those are all 64-bit registers. But you can also actually use them in a 32-bit context if you use W to reference them by. And that will essentially just ignore the upper 32 bits, acting as a 32-bit register. The link register on ARMv8 is on X30. And then we have a stack pointer, which is its own register, and a program counter, which is again its own register. This time, it's actually slightly different. You can't directly modify the program counter register on ARMv8. You have to use the branch instructions, unlike ARMv7. So for example, if you wanted to, in ARMv7, you could actually move any value you want into the program counter for an assembly program. But ARMv8, that doesn't work. You have to actually use the branch instructions if you want to alter the code execution flow. So here's a quick illustration to highlight some of the differences. So these two very short code snippets are doing the exact same thing, one for ARMv7, one for ARMv8. So you can see there's difference in register names. The instruction mnemonics vary slightly, and there are some additional ones in ARMv8. And then return instructions. So with ARMv7, we branch to the link register, and in ARMv8, you get a ret instruction, which actually does the exact same thing. For stack access functions, if you want to push an item onto the stack, on ARMv7, you have an actual push instruction. So you just specify the registers, and then that will be placed on top of the stack for you. ARMv8, you have to take two steps to this. So the first one is a sub instruction. This basically takes away a value from the stack pointer, which allows the stack to grow in size. It adds some new space at the top. And then you use an STP instruction, which stores a pair of registers, and then you just reference the stack relative address, and it will place them on the stack. So you have to kind of go 2 stages instead of 1. And then a similar thing happens for the opposite, so for returning and for popping items off the stack. So with ARMv7, you have a pop instruction, which takes items off the stack and places them into the specified registers. And in this case, you can actually use this as one of the possible return instructions on ARMv7, because you can see there it's popping a value into the program counter. And as I said, that's not possible on ARMv8, but that is one of the return instructions on ARMv7. And in ARMv8, this time there is 3 instructions. So again, we do the opposite we did before. You load a pair of registers from the stack relative address. Then you add a value to the stack pointer to shrink the stack back to its original size. And then finally, in this case, we're returning from a function, you ret, which branches to X30, which you would have just loaded from the stack there. So that's the basics of the ARM and ARMv8 architectures out of the way. Now I'm going to go over the basics of ROP. So ROP stands for Return-Oriented Programming, and it's a modern exploit technique used to execute payloads on your target process. So it works as a code reuse attack method, and which was originally designed as an alternative to using shellcode payloads, which some of you may be familiar if you've ever done any kind of exploitation on very old systems. So shellcode was the old-fashioned way of writing these payloads, and it basically works by taking some assembly instructions, finding the actual byte encoding of these instructions, and then writing them to somewhere in the process memory. So you could write them on the stack or the heap, and then you would basically use your code execution bug to jump to the location they're stored in the memory, and it would then go through and execute your own code in the target process, and you can do whatever you want, basically. But with modern systems, there are some simple protections against that, which we'll go over in a minute. So here's an example. If we have one of these very basic kind of classic example programs you see with a buffer overflow, if we have this 32-byte char array buff, this will be stored on the stack. And then stir copy obviously is a vulnerable function. It doesn't have any bounds check-in on it. So if you were to copy argv1, the user could have entered a huge string, and it's going to try and fit all that into the 32-byte char array. And since that's on the stack, it's going to overflow past the bounds of the 32 bytes, and it will overflow into the return address and allowing you to take control of the program. So here is a diagram representing that overflown stack. So at the top, you have the overflown data, which is all the shellcode. So these are the byte representations of those instructions. and then you get down here where it says payload address, you overwrite this. This is the return address for the function, and you just need to overwrite that with the address that points back to the top where your shellcode starts. And then when the current function returns, whatever that is, it's going to jump to your shellcode, and it's going to execute your code within the target process. But on a modern system, as I said, we have data execution prevention, which essentially prevents any data ever being executed. So this works by disallowing memory pages to be both writable and executable at the same time. So you can only have read and execute or read and write. So that's obviously not possible on any modern systems today. So if you actually want to use execute a payload on a modern system, you have to use ROP, and that's how it provides the workaround. So the way this workaround works is is using legitimate instructions in a different order, in a different context. So you can obviously execute legitimate instructions because they're in the text segment of whatever target binary you're looking at. So you have to use these instructions, but you just basically take parts of code from different functions in different areas and piece them together in your own order to essentially create the same outcome that you would want with your shellcode payload. And this works by chaining together gadgets, which are, we'll cover that in a minute. And because of this, because they're using real instructions in a different order, obviously the data execution prevention doesn't matter because they are actually allowed to be executed because they are real instructions. So gadgets are short sequences of instructions that are found within the actual binary, and they end with a return instruction. And this return instruction is basically what allows you to connect together loads of gadgets and create a full payload. So they're obviously found within the text segment, as I said, because they have to be executable. And since they do end with the return instruction, they're normally found at the end of a function because that's where you'd find return instructions. So this is an example of a gadget you might find when working on a payload. So this is in the ARM64 assembly. So this gadget consists of 3 instructions, and the first one is an str instruction. So this stores the value of a register at a specified location. So in this case, we have x0 as the data. So whatever data is currently inside of x0, it's going to be stored or written to the memory location pointed to by x1. So why would you want to use this? Well, if you're an attacker and you want to patch some part of your target process, or you want to change some variables in there to give you some new functionality, then assuming that you can control both x0 and x1, this instruction essentially will patch your arbitrary data to whatever address you want. So in the context of something like an iOS kernel vulnerability or a kernel exploit, the original patches are actually done using these kind of instructions. So if you want to patch a variable to allow or disallow code sign-in, you could write your data to x0 and then write the address of the part that holds that variable, and then executing this gadget is going to overwrite the data and it will patch the variable. The last 2 instructions in this gadget are actually not really part of the gadget itself, but they're just used as the return instruction. So we load values from the stack, and then you return which branches to x30. And that's how the gadgets will be chained. So this gadget chaining, as I said, it works with the return instructions. And the way you actually do this and actually get the chain executing in chronological order is by storing all the addresses of all the gadgets you want on the stack in the chronological order. And every time a return instruction is executed at the end of a gadget, it's going to automatically be going to the next address on the stack because that's how return instructions work. And it's going to be continuously jumping through your payload. So for example, again, if we have the overflown stack again, this time there's no need for shellcode, so we just fill it up with junk to overflow it. And then we get to the save return address part. This time we overwrite that with the address of the first gadget. So this gadget, if you follow that gray arrow, it points to some gadget in the binary, it doesn't matter what it is. The point is it ends with a return instruction. So essentially what will happen in this case is when the function returns, it's going to jump to your first gadget, your gadget's going to execute, and then it's going to return, which is going to then go back to look for the next return address on the stack, which if you set that up, it's got a second gadget there. This will then continue, go to the next gadget, and so on for as many gadgets as you have in your payload. So some annotations on that. So how do you actually find gadgets if you're building a payload for a real exploit? So the easiest way to do this, obviously you know that they need to have a return instruction at the end, so you can just scan the whole binary for return instructions. And when you find a return instruction, if you search backwards in 4-byte chunks, you'll see the instructions that come before them. And you just basically need to look for useful instructions depending on what you're trying to achieve. And there's a lot of tools out there that will do this for you, actually, so you don't have to do this manually. They'll just do it automatically. So there's a few links if you want to look at some of them. So with complex ROP chains, in most exploits, or at least used in kind of weapons-grade malware and things, you're going to want to be doing a lot of stuff with your ROP chain. You're not just going to want to jump to one place. So you're going to need to use several hundreds of gadgets, maybe in some cases. So with the kernel patching, for example, it would take quite a few gadgets to be preparing patch values and addresses, and then jump into the patches each time. So you will need significantly quite large ROP chains. And there is actually a problem that will arise if you're doing this on a modern system and if you're working with modern vulnerabilities. So all vulnerabilities are different, and with the example I showed a minute ago, that was obviously a classic stack buffer overflow, which realistically doesn't actually occur anymore in real-world systems, at least not in that way. And a lot of the gadgets, at least the ones I've studied, a lot of the vulnerabilities, at least the ones I've studied in modern systems such as iOS, these are all mostly based around heap vulnerabilities. And these kinds of vulnerabilities can actually limit the amount of gadgets that you can execute. And some of them actually only allow you to have one gadget worth of execution. So, for example, if you have a heap overflow as opposed to a stack overflow, you can overwrite a function pointer maybe on the heap and jump to a gadget. But as soon as that gadget tries to return, it's going to be returning to the stack, because that's how return instructions work. And since you're not working with a stack-based bug, you have no control over the stack data. So your program will basically terminate after your first gadget, which is useless, really, because you can't do much at all. So there's a solution to that, which is stack pivoting. So this basically works by creating a fake stack on the heap, or in whatever memory you're working with. And this works by basically changing the value of the stack pointer so that it points to somewhere new. And then you populate this memory with your gadget chain, your addresses. And then this time when you return from your first gadget, so you execute your first gadget, it's going to return. It's then going to actually be returning to your fake stack on the heap, and therefore you do have control over the data. So to understand exactly how that works, you first need to understand exactly how the stack works at a lower level in terms of how it actually executes and works in the memory. So theoretically, what you get taught in most computer science classes is that this stack is a physical stack of items, so such like plates or something, so you can add items to the top and remove them from the top. So in reality, though, this is actually just a kind of abstraction. So, for example, you learn about push, which adds an item to the top of the stack, and you learn about pop, which removes an item from the top of the stack, but you never really get taught how that's implemented in an actual program. So it's an abstraction, and in reality, the stack doesn't actually exist as we imagine it like that. It's actually just some area of memory. It's nothing really special. The only thing that makes it the stack is the fact that the stack pointer register will point to the top of it. So, for example, this is a more realistic representation. So if we have this block of memory here, and you can see the stack pointer there is set to address 10, which is where the red arrow points to. And this memory is just normal memory, but the stack is essentially considered the stack because that pointer points to it. So if you actually want to do a push or pop instruction in this way, all you're basically doing is modifying the stack pointer value. So for example, if you want to pop the top item off the stack, you would add 4 to the stack pointer, and it's going to be pointing higher up in memory but lower down the stack, because the stack grows in the opposite way to what you might think. And that, therefore, now it's actually, the stack is 1 item shorter. The memory doesn't need to be cleared, but that's basically how these instructions manipulate the stack. And then the same thing goes for pushing. So you basically do the opposite. You would subtract 4 from the stack pointer for every value you want to push, and then you write your new data to these addresses. So so with that knowledge in mind, you can understand how a stack pivot works in an exploit. So if, for example, you have the stack here in your process memory, let's say this is the whole process memory, and you have the stack here, and you can see the stack pointer and the stack base. So that pointer is currently at the top of the stack. And then let's say you have your heap memory with data you fully control. So here what you can do is put all your gadget addresses as if it was on the stack, and then you use a special type of gadget to basically move the stack pointer so it points to your heap memory. And then this is going to allow, this basically means the program is now going to treat that as the stack, and therefore your ROP chain can be executed. So this whole block basically gets treated as a stack. So how do you actually do that in practice? Well, you use a special type of ROP gadget, which is called a pivot gadget. And all this needs to do is change the value of the stack pointer to something that you can actually control. So there's an example here of a stack pivot gadget. So you can see, again, this gadget consists of 3 instructions. You have a move instruction, which moves the value of x5 into the stack pointer. So if x5 holds an address to some memory you control, then it's going to move that to the stack pointer, and therefore that's a successful stack pivot gadget. And again, that's just to return from the gadget. So with all that knowledge in mind, I'm going to go through a quick example attack on a demo program that I wrote for this talk. So you can kind of see how this actually works. So this program is called Codetalks demo, and there's an ARMv7 and an ARMv8 version, and I'll probably upload this somewhere afterwards, so you can actually try this if you're interested. And you see the description there. It's just a small binary vulnerable to a heap buffer overflow, so not a stack-based one, a heap one, and that will allow us to overwrite some function pointer. And the aim of the exploit, we're going to try and exploit this, and we're going to call a secret function, which is a function that just lies within the binary. It's not actually used. It's not called anywhere. It's just sort of unused code sitting in there. And we need to call the secret function, but pass a special code as the first argument to it, and then we should get a root shell, basically. So here is what the program looks like if you run this. So you can see basically it prints out a little banner, Codetalks banner, and then asks you to enter the path to a data file. So you can enter like file.txt, and it basically reads out all of the data and processes it, and then tells you that the data is valid, and then quits. So that's all it does. So obviously you can probably already tell the only place the overflow can occur is with reading the data out. So that would be right, because here's a pseudocode snippet of the vulnerable part. So this call to fread is reading out 512 bytes from the file, but it's trying to store it into a structure on the heap or in a char array that's only got 64 bytes. So what's basically going to happen is, if you can see up here, this is the data that will fit in the 64-byte buffer, but any data that goes over that is going to overwrite that function pointer, because right after it, we have a function pointer stored on the heap as well. So it's very simple to trigger this bug. You just need to have a file that's more than 64 bytes long, and it will automatically overwrite into that function pointer. And conveniently, that function pointer is actually called directly after the call to fread. So it's a very artificial kind of setup, but it will represent a vulnerability for us. And then here's the C code equivalent if you want to see how that actually works. So the secret function, this, as I said, is the function that is in the binary but never used. And this is basically all its job is to do is to validate a code passed as its first argument. So on the ARM and ARMv8 instruction sets, as I mentioned earlier briefly, arguments are passed in registers. So the first argument would be in X0 or in R0 if you're on 32-bit. And that's all we need. So the first argument is going to be in X0. So what it basically does is it checks against a certain code, and that code is actually outdated. That's from a different version of this talk, but the code in this example is 1234 in hex. And what it does is basically compares it against the first argument. So you can see it's comparing it against W0, so the 32-bit version of X0. And then if it succeeds, so if it's a valid code, it's going to branch you to this section, which will give you the root shell. And if it's not, then it's going to tell you if you got it wrong. Now, I know you're probably thinking, why wouldn't you not just jump here? Because you wouldn't even need a ROP chain to do that. You could just actually control code execution and jump straight there and get the root shell. But that's just too easy. And the purpose of this is to demonstrate how a more complex ROP chain would work. So it's not actually a real-life exploit. Obviously, if you're doing this in real life, you would just do the easiest method. So we're going to assume we have to call secret from the actual entry point of secret. So the plan is going to be as follows. We're going to gain code execution with the bug that we already know how to do, which is just by reading in a very large file. And then we can override the function pointer with some crafted data that's going to point somewhere. Then what we want to do is obviously use return-oriented programming to prepare X0 or W0 to hold the secret code. And then we just need to jump to secret, which will then hopefully validate it and give us the root shell. So as I said, we know we can control the program counter or the code execution flow by overwriting the pointer. And we know that we can execute only a single gadget because we're working with a heap-based bug. So after the first gadget, it's going to go straight back to the stack. So we obviously do need a stack pivot. And the stack pivot criteria, it must again be a single gadget because that's all we get to work with. And it must allow us to point the stack pointer to the start of the heap buffer, which we obviously will control because it reads out data from a file that we fully control. So this is the gadget we're going to use. It's the same one as earlier. And what it does, as I said, moves the value of x5 into the stack pointer. And you may be wondering, why does x5 hold the valid address? Well, I actually deliberately wrote this program, so I made it as simple as possible. So I deliberately prepared x5 so that it will hold the address of the heap object, just to keep things as simple as possible. So we've got the stack pivot sorted. Now to load x0 or w0 with the code, we need some more gadgets. So here are actually 2 gadgets. So I did this deliberately to kind of replicate how real-world payload construction is with ROP, because obviously you have to use the gadgets or the code that's actually in the binary. You can't write any of your own code because then you won't be able to execute it. So you have to work with what you've got. And often it will be the case that you can't find a gadget that does exactly what you want it to do, or it kind of does what you want it to do sort of, but it gives you some side effects, or it just is not as straightforward as that. So in this case, we have 2 stages to control x0. So the first gadget allows us to control x3 and x4 by loading values from the stack, which we'll control because that's on our fake stack now on the heap. So we can use this gadget to control x3 and 4, and then it will return. And then we have another gadget, which is going to move x4 into x0, which x0 is the one we actually want to control, and we would have just controlled it x4 with the first gadget. So this gadget will then control x0, and again, it will return. So it's just sort of taken in 2 stages rather than having 1 gadget. So that's all done. And then finally, calling secret from its entry point. That's as simple as just knowing the address of secret. So that's also done as well. So here is an actual crafted payload. So this is a hex dump of a file that will exploit that program and carry out all the ROP. So I'm going to quickly dissect what this does. So first of all, this whole file, this is less than 512 bytes. So all of this is going to be written to the heap chunk because it's reading out 512 bytes and it's not gone over that. So all of this is going to be put on the heap. The first 64 bytes is going to be put into the buffer, so it's going to fit nicely in the buffer, and that means that anything after that is going to overwrite that function pointer, which is this. And this basically points to the first gadget, which is the pivot gadget. So sorry if I'm going too fast on this. I've only actually got 5 minutes left, so I'm just trying to go through this a bit quicker. But this will point to the pivot gadget, which is going to be the first thing that's going to execute. And that's then going to change the stack pointer to essentially point to the top of this file, because all the data in this file is on the heap. After this gadget executes, the top of the stack is now the top of the data in this file. So the next return data will be pulled from this top of the stack. So x29 is a register we load as well, but we don't actually need that. So that's just junk. Then the next gadget address is going to go into x30, because that's where we want to jump to next. And this is going to hold the address to the gadget 2. Which is going to prepare x3 and x4. Then we have some more junk for x3 because we don't want to control that one. The actual secret code itself, it goes into x4. So that's 1, 2, 3, 4. And by the way, this is all in little endian. That's why the bytes are in reverse order. Then we have some more junk for x29. And then the third gadget, which will actually move x4 into x0. And then some more junk to x29. And finally, the address of the secret function itself. And then we're back to where we started. So hopefully that made sense. If not, then you can actually download this online and work it out yourself how it actually works, if I went too quickly. But anyway, so here's what happens if you actually run that file. So you run the Codetalks demo app again. You specify the exploit payload file, and it's going to read it in, process the data. All of the ROP will be carried out, and the secret function gives you that root shell. So that is basically it for the demo. The exploit's complete. And yeah, if you want to learn any more about like ARM exploitation or software exploitation in general, then you can look at these links here. There's a few good ones to get started with the basics if you've never done it before. And yeah, that's my Twitter handle if you want to follow any of the work I do, or if you want to ask me a question after this, after the conference. But yeah, I'm happy to answer any questions you have now as well. So yeah, thank you.
Hi, so thank you for the talk. My question is, how did you actually get the address of the stack pivot? Because usually you need an information leak for that, right? In this case, it was artificially constructed, I guess.
Yeah, so actually, yeah, I wouldn't have had time to cover all of this in one talk, so I kind of deliberately missed those bits out. But yeah, in a real-world exploit, you would have a lot of other things to also deal with. So ASLR, which would actually randomize the address of everything in the binary. So you wouldn't know where anything is, any of the gadgets at all. So yeah, you would need an information leak bug as well, but I did deliberately miss that out of this talk just to keep it as short as possible.
Okay, so it was just disabled.
Yeah, in a real world case, you would need it. I'd actually disabled ASLR for the demo.
All right, thanks.
Any other questions?
Hey, thanks for the amazing talk. I just have a question regarding address space randomization. So if the actual address is randomized, then I have a problem, I guess, right?
Yeah, so basically ASLR will, every time you run your target process, a random value is determined, and this is then used, basically it's added to everything in the binary. So the whole target address space, if you were looking at it in a disassembler as a static binary, when it's actually running, it has an ASLR slide added to it. So the whole thing basically gets shifted. So all the addresses are still relative to each other, so they're still just as far away from each other as they would be in the actual static binary, but they are slid randomly on each run of the program. So you can use, to get around that, you would need to use an information leak bug. So that's a separate vulnerability. And you basically, that can work by leaking some pointer from the stack or from anywhere really. And if you find one pointer, you can essentially find out the address of everything in the binary, because if you know what the pointer is, where it's come from, you just subtract one from the other and find the difference, and that difference is the ASLR slide. And then you just add that slide to any other gadget address you want, and that's the real-time address of it, basically.
Okay, thanks.
Any other questions? No. All right, I think that's all then. All right, thank you.